In this video, we will begin discussing something called the integral test. The integral test is going to be first of many tests that we have that will allow us to check and see if a given series converges or diverges. And the integral test tells us the following. If we have the function f, which is associated to the sequence we are summing up to form our series, and if the function f satisfies some key properties, it needs to be continuous, positive, and decreasing on the interval from 1 to infinity. Then the connection is that the series itself is going to converge if and only if that associated improper integral converges. And furthermore, thinking back to our previous videos, this seems like a really natural connection, thinking about how we define more precisely what it means for a series to converge or diverge. It was based upon taking a limit as n approaches infinity of a sequence of partial sums, which in nature is very similar to how we have calculated improper integrals. As a side note and very important observation, in order to use the integral test, you always need to verify that these hypotheses are met. That is, you specifically have to write down what the function f of x is and state why it is continuous, positive, and decreasing. You usually get the continuous and positive almost for free. It's a matter of writing them down. As we'll see, the decreasing, sometimes we might need to write a few more details down. So let's use the integral test to determine whether the given series converges or diverges. So the first thing we need to do is make sure that we are allowed to use the integral test. That is, what is the associated function? Does it satisfy the desired hypotheses? So our associated function in this case, f of x, is 1 over x cubed. And we're thinking specifically about the interval from 1 to infinity because this series starts summing at 1. Well, 1 over x cubed is continuous everywhere away from 0, so it's certainly continuous on that interval from 1 to infinity. It is positive on that interval, because if x is positive, 1 over x cubed is positive. And I'm going to go further and just go ahead and say that it is a decreasing function as well. And to see that it's decreasing, a bit more intuitively, we can say it's decreasing because dividing by bigger numbers will give you a smaller output. Or maybe a bit less intuitively, you can think in terms of calculus. If you were to calculate f prime of x, that would be minus 3 over x to the 4th, which is always negative. And if the first derivative is negative, that implies the function is decreasing. So at this point, we have that the hypotheses of the integral test are satisfied, so we can apply the integral test. And the integral test tells us that to determine the convergence or divergence series, we look at the associated improper integral. So we would like to evaluate the integral from 1 to infinity of 1 over x cubed. So in order to evaluate an improper integral, our first step is to write it as a limit. So the limit as a approaches infinity, the integral from 1 to a of 1 over x cubed. The antiderivative of 1 over x cubed is minus 1 over 2x squared. And we're evaluating this from 1 to a. So we plug in an a, we put a minus sign, we plug in a 1. So when you plug in the 1, it's going to be minus a minus, so a positive 1/2. And when you plug in a, you're going to have the negative there, so 1 over 2 a squared. And now when we take the limit as a approaches infinity, the second part goes to 0, and what we are left with is simply the number 1/2. So the associated function f satisfies the hypotheses of the integral test. It's a continuous, positive, decreasing function on the interval from 1 to infinity. The associated improper integral converges, so by the integral test, the series which we are interested in, the sum from k equals 1 to infinity, 1 over k cubed, also converges. And an important point to keep in mind, and something that we'll see many times in future videos, is whenever we are talking about the convergence or divergence of a series, we should make sure to give a detailed conclusion. The given series, you should be telling us, does it converge or diverge, and specifically by what test. And with the integral test, you're always more than welcome to abbreviate it with just capital I, capital T. Another example. Let's use the integral test to determine whether the series given here converges or diverges. Note in this case we are starting our sum off with k equals 2. The reason being is that natural log of 1 is 0, so it doesn't make sense to start at 1. It would be an undefined quantity. So let's think about the associated function. So the associated function in this case, change each k to an x, 1 over x ln of x. This function is continuous as long as you stay away from where the denominator is 0. That is, if you stay away from 0 and 1. So this is continuous. And now instead of thinking about the interval from 1 to infinity, we're going to think about 2 to infinity because 2 corresponds to that lower index of the summation. Okay, on this interval from 2 to infinity, we have a positive function. So as mentioned previously, no details for the continuity and positivity need to be given. It's more a matter of just writing down those pieces of information. Similarly here, I think we can just note that this is a decreasing function. The reason being is as we plug in larger values of x, what's in the bottom is increasing, and dividing by something bigger gives you something smaller, hence decreasing. If you don't see that, you could just as easily take the first derivative and note that it's negative. And now that we know the hypotheses are satisfied, we can go ahead and evaluate the associated integral. So in this case, because the lower index starts at 2, we are going to be evaluating the integral from 2 to infinity of 1 over x ln of x. Because it's an improper integral, our first step is to rewrite this as a limit. So the limit as a approaches infinity of the integral from 2 to a of 1 over x ln of x. And this integral is something that we have previously evaluated, but the observation to make is based upon the ln of x and its derivative 1 over x. We see that one could use a substitution u equals ln of x. With this substitution, you should very quickly be able to convince yourself the antiderivative of 1 over x ln of x is going to be the ln of the absolute value of the ln of x. So we need to plug in an a, put a minus sign, plug in a 2. So we're going to have the natural log of the natural log of a minus the natural log of the natural log of 2. And note, as a goes to infinity, the natural log of a is going to infinity. So this limit is infinity. So in the language of improper integrals, we would say that the given improper integral diverges. Therefore, by the integral test, this associated series is also going to diverge. So by the integral test, or IT for integral test, the sum from k equals 2 to infinity of 1 over k ln of k diverges.